So matrix multiplication, this is the usual way of doing things, inner product way. So C of ij, Cij, that is any element ij, is equal to the ith row, inner product of the ith row and jth column. Now let us do it using outer product. Where the outer product is actually. So what I'll do is column of A times rows of B. This is how I'll be doing. Column of A times rows of B. And what exactly this will give me, let us see. So let me take one column and one row here. Let me write it here. A 1 1, A 2 1, A 3 1. This times B 1 1, B 1 2, B 1 3. So this becomes 3 cross 1. This is 1 cross 3. I've taken only one column and one row. 3 cross 1, 1 cross 3. And this itself gives me a 3 cross 3 matrix. And in fact, it is the same thing what we have seen in the very first class. Like where is that? Yeah, this one, this red color. Each column is scaled by some scalar quantity, and then they are added together to form the final matrix. Now the same thing I am doing here. Each column of matrix A is scaled by each element of the first each element of the one row of B matrix, and then sum it together. Now let me write it. This would be very much clearer in that case. Sorry. A11, B11. This is, and the second element becomes A11, B12. Third element is A11, B13. A21, B11, A21, B12, A21, B13, A31, B11, A31, B12, A31, B13. This is for one row, one column and one row. This is what we have got. So what is the meaning of this? I do the same thing for the second column, second row, third column. In that way, I can and add them together. Finally, I get the matrix. That is how it can be done. But then let us try to understand what is the meaning of this. Can you infer something from here?
Sir, if we say that the first column is a vector, then it is scaled b1 times. The second column is scaled b1 2 times, and third column is scaled b1 3 times.
Okay, that's correct. And in the same thing can be said if I say B is a vector and A11 is a scalar quantity, A21 is a scalar quantity, A31 is a scalar quantity. That's right. And that way I can say. Any other insights? Tell me in terms of rank. What is the rank of this matrix? What is the rank of this matrix?
One.
That's right. It is 1. Look at the columns. Look at the columns of this C matrix. This is let me say this is uh, A B. No. Don't let us not say A. Let me say this is U because this is one sub part of one part of the A matrix. Let me say one column vector of A, one row vector of B. So let me say this is V transpose. So U V transpose, this is U V transpose. So look at the columns of U V transpose. What are the columns of U V transpose? What are they? The columns of U V transpose are multiple of one particular vector, that is U. As you know, rank is number of independent column spaces and independent row spaces. So number of independent columns or number of independent rows, here in both the cases it is equal to 1. So the same thing I can write here, rows of UV transpose is nothing but multiples of now the insight is this. This is what the understanding is. Rank 1. This is important. What if two big matrices are given to me? I break them into smaller constituents of rank 1 matrices. Each small constituent is having one independent vector. And I analyze them each independent vector individually. You will uh, you will not realize how powerful this idea is actually. Particularly in the case of machine learning, signal processing, image processing. I mean, no matter whatever area you call, this this very thought is very powerful. It's a very powerful one. Okay. So just for the sake of completeness, uh, let us see this one. Let me write it as one small 2 cross 2 matrix. 1 2 0 1. Another 2 cross 2 matrix. Let us say 4 0 2 5. So this outer product way, if I go, so this becomes 1 0 4 2 4 0, sorry, 4 0 plus so how much this is? This becomes 4 0 0 0 4 10 2 5. So this becomes 8 10 2 5. Okay. So each one of them is a rank 1 matrix. That is how it is. But then if you see the number of matrix multiplications, number of multiplications and addition in both the cases, it is same. If you say row times column, so this becomes, let us say this is the matrix size is, let me write it in this way. We have matrices like M and P. So if I say it is row times column, this becomes actually MP uh, inner product and in each inner product, you have mm, MP, yeah, N multiplication and products. So total it is M and P. Whereas if it is column times row, this is actually N outer products, and in each outer product you have MP products. So again it is M and P. So cost wise both are same. There is no difference between them. So having said all this, can you tell me uh, if two matrices are added, let us say A is a matrix and B is a matrix. Uh, A is a matrix, B is another matrix. Rank of A is known, rank of B is known. What will happen to the rank of A plus B? Just think about it. What is a rank? Rank is the independent number of columns or the rows. Let us talk about independent number of columns. So you have some number here. Let us say n, n1, na, let us say, and here nb. So na number of columns, independent columns, and b number of independent columns. Here what will happen?
Less than Na plus Nb.
Na plus nb?
Less than Na plus Nb.
Yeah, that's correct. That's correct. So the rank of A plus B will always be less than equal to Na plus nb. Na plus nb. And now you know the reason why Na, it will be less than equal to Na plus nb. Like you have Na number of independent columns, nb number of independent columns here, and Na independent vectors, nb independent vectors, when you are adding together, they may be completely independent. Na and nb number of vectors, they are completely independent, or some of the vectors of B would be part of A as well. So sum of complete mutually exclusive number of vectors, independent vectors, would result in always equal to. Otherwise, it will be less than. So what about what if A is an identity matrix and B is an identity matrix?
One.
Yeah, A is an identity matrix and B is an identity matrix. In that way, um, what is the rank?
Size of the matrix.
Size of the matrix.
Young.
Sir, it will be 1.
Rank will be 1.
No, sir, size of the matrix.
How come it will be 1? One zero zero.
Sorry, it will
0,
be rank of, it is equals to the order of the matrix.
That's correct. That's correct. So here you have all of them are independent, and there is the size of the matrix. So this is also A is also identity and B is also identity. So in that case, it will remain the same. What about A times B?
Same order of matrix.
No, I'm not talking about any identity matrix. I'm talking about a matrix A, matrix B, which has got rank A, rank B, respectively. So what is the rank of AB? You forget that it's an identity matrix. It's any usual matrix, A and B. Fundamentally, what exactly we are doing in multiplying, while multiplying? We are scaling, isn't it? Whenever we are multiplying two matrices, fundamentally or essentially we are scaling one vector with the scale of the scalar quantity or the elements of the other vector. That is what we have understood in last couple of classes. The columns of A, it's scaled with the elements of B matrix. That is the scalar quantity of B matrix. This is what we have been observing. And in today's class, with the outer product concept, it has been scaled, then it has been added. So uh, it has been scaled, then it has been added. So while adding, this is what the scenario is. But while scaling, what is the concept? The number of columns of matrix A, if I scale, whether the nature of independence will alter. There is a matrix A, it has got 3 cross 3 matrix. It has got two independent columns, and those two independent columns I scale with some scalar quantity. Will their independence nature alter?
No, sir.
No, they are not going to alter.
No,
So, so, so the rank of AB will be always less than equal to rank of A.
A.
And in the same way, it will also be less than equal to rank of B. In either way you talk. So this both are correct. Okay. So in other way, we say that mm, how do I represent that? That is what we call is a every the columns of A, the columns of A is a combination of the columns. The columns of AB, the columns of AB is a combination of the columns of A. And here the rows of AB is a combination of the rows of B. In that way. Or if I take the C notation, that is C of AB. And here C is not that C matrix. C means here I am telling column matrix. Column space. And in place of writing rows of AB, this mathematician usually make things a little bit complicated and they write it as C of AB transpose. Same thing only. They don't want to have another notation as column space, row space. Instead, they make it as column space of AB transpose. So column space of AB, column space of AB is within the column space of A, and column space of AB transpose, column space of AB is in column space of A, or similarly column space of AB transpose is in column space of B transpose. This is just another way of denoting the things. Okay, so let us stop here today, and I hope things are I know the things are moving a little bit slow, but then yeah, subsequent times we will catch up.
Hello, sir.
Yes.
Sir, the last two conclusions you made, sir, those are true for when we are multiplying A and B with outer product, right?
No. And if you say like that, prior to that, we saw that outer product, matrix multiplication with outer product and matrix multiplication with inner product, both are same. They do not result in two different answer.
So then, column space of AB, sir, when you write column space of AB is in column space of A, sir, is it same like column space of AB is in column space of B?
No. I've written transpose. I've
Sir,
written
actually,
transpose.
when we are doing multiplication, we are multiplying first means row of first matrix, then column of the second matrix. So why is the column space of AB is in column space of A and not in B?
Oh, so for that, this statement and this statement both are same. Do you find any difference between these two statements? And similarly, this statement and this statement. Now, if I hope this is understood, right? This this
Yes, sir.
statement is understood. Rank of AB is less than equal to rank of A.
Yes, sir.
If this is understood, then this is the same thing only I've written.
So basically, when you say rank of A, you refer to number of independent columns of A, right?
Yeah, of course.
Okay, sir.
Sir, actually,
Independent
sir,
columns of A or independent rows of A. Yeah, tell.
sir, if when we say rank of AB is less than equal to rank of A or rank of AB is less than equal to rank of B, then we are assuming that rank of A and B are both same. What if the ranks of A and B are different?
No. Did I say that rank of A and B are same?
No, sir.
No. Rank of A, that's what I wrote it here, right? Rank A, rank B. Let us say there are N A number of independent columns, N B number of independent columns. N A and N B may be equal, may not be equal. You have you have two 3 cross 3 matrices, and the matrix A comprises two vectors, two independent vectors, not two vectors, two independent vectors. Let us imagine the 3D space. Just imagine the 3D space. It comprises two independent vectors. Third vector is a multiple of the first one or the second one or a combination of that. But then matrix A has two independent vectors in the three-dimensional space. And matrix B is one independent vector, is having one independent vector. Now, matrix B, okay, let me draw it in this way. That would be much better. Let me draw it in this way. Let us say, so I have matrix A. Let me put matrix A in blue color. So matrix A is having one vector this and another vector this. These are two independent vectors. And you know the column space between these two. This is the column space of A, okay? Matrix A, or the column space of independent columns of matrix A. Then let me put it in green. Now you have matrix B, which is having an independent column. Only one independent column is there. Okay, this is one scenario. Another scenario would be this. Okay, so NA is equal to 2 and B is equal to 1. And this 1 is independent from these two blues. This is one scenario. So second scenario is this 1 is a linear combination of these two. That is also possible. And accordingly, you get this answer. If it is the first case, all the three are independent, this becomes 2 plus 1. Otherwise, it still remains 2. I hope it is understood.
Yes, sir.
So finally, the takeaway of this year is like break the entire thing into rank 1 matrices and start attacking and what? So break the matrices into rank 1. So this is what the entire concept is. Multiplying the matrices A into B into a series summation of rank 1 matrices. Multiplication of two matrices is nothing but series summation of rank 1 matrices. Now you have rank 1, that means only one vector you have to play with. Only one vector that you need to play with. Now, there are numerous possibilities here. If you have this kind of scenario of rank 1 matrices, you have numerous possibilities. The problems become tractable. You can easily find out which are the other rank 1 matrices or which are the other independent vectors that are multiples of the previous independent vectors. We can easily eliminate any redundancy in the matrices. I mean, redundancy would be a new term for you here in this case. We'll talk about this later. So there are numerous possibilities. That is what the takeaway is with rank 1 matrices. So with that, we come to an end of this year. Wish you all probably happy new year and hope to see you soon, guys. Thank you.
Thank you, sir. Wish you the same.
Thank you, sir.